Okay, the next problem, 35, wants the mass rational function with this graph. I didn't include the graphs here, but once again, this should be pretty straightforward on the exam because you have your calculator, so you can always just graph it, see what it looks like. You could also do some algebra to combine this. I think if you do, you get like 3 minus x over 4 minus x or something. I don't know, something like that. And then y equals -1, if you do the ratio of leading coefficients, would give you this horizontal asymptote. So you could, use your algebra rules that are in your formula sheet and graph it in your calculator, all of which will give you the right graph for this. Okay, this next question is a good question. If we were to simplify this function, write it as x minus 3 over x, or times x plus 3 all over x minus 3, I just factored the numerator into a difference of 2 squares here. Still my f of x. You'll notice that these cancel and I get x plus 3. So basically what that means is these two functions are identical, f of x and g of x, except for one point. And that one point is obviously the whole. We get wholes from the factors that cancel. So what happens is this original function as a whole at x equals 3. And I can graph that and show you that real quick. Alright, so the blue one is the first one and the pink one is the second one. They look virtually identical except for if you go to your table, go to second table, and we know that at x equals 3 as a whole, there it is. X equals 3, the first function has an error there. And it makes sense because when you plug in 3, you get 0 in the top and 0 in the bottom, and 0 divided into 0 parts doesn't make any sense. So that's why it's a whole. So to quickly answer these questions, the domains equal no, because this is all real numbers, and this is all real numbers except 3. Does f have a vertical asymptote? No, it's got a hole though. And then explain why the graphs appear to be identical. Well, because they're basically the same line, except for this one point. So are the functions identical? No. They have a discrepancy at x equals 3, basically, is what you could say for that. Next problem wants to write an equation for the quadratic function whose graph contains the vertex and point. I would use vertex form for this. And it doesn't say what, it says write an equation, it doesn't say what form to put it in, so we can leave it in this form when we're done. Double negatives cancel when I stick h of -2 in. K is -3. And they also give me one of these points, 1, 2, so I'm going to stick 1 in for x and 2 in for y and solve for a. So this would be 3 squared, which is 9. And then I can solve by adding 3 to both sides and dividing both sides by 9. So my a is 5/9. So I can plug that back in. 5/9 goes in for a. My h is -2, and my k is -3. So there's my function in vertex form. We could FOIL it out, put it in this, what we would call standard form, but what I've called standard form anyway. But this is good enough. Okay, this just wants us to do the division here and write the summary statement. So we have x squared plus 0x plus 4, and we're going to divide that into this big polynomial, 2x to the 4th minus 3x cubed plus 9x squared minus 14x plus 7. Okay, so the first thing is what do we need to put to x squared to get 2x to the 4th? That'd be 2x squared. When you multiply, you get 2x to the 4th. And when you follow through, you get 0x cubed and 8x squared, so we can subtract everything. So you get -3x cubed, and 9 minus 8 gives you 1x squared. I can drop down the new next term, -14, and then start over and say, what do I multiply by x squared to get -3x cubed? That'd be -3x. And then follow through. -3x times 0x gives me 0x squared. And -3 times 4 gives me -12x. And when I subtract, I get x squared minus nothing gives me x squared. And then -14x minus -12 gives me -2x. And I can drop down to 7. And the next question becomes, what do I multiply by x squared to get x squared? That'd be 1. And then follow through. 0x. This would be plus 4. So when I subtract, I get -2x. And I get 7 minus 4, which is 3. So there's my remainder. So to write the summary statement, I guess basically what I could do is just say this plus, let me change colors again, plus the remainder, -2x plus 3 over the divisor, x squared plus 4. So there's my quotient plus remainder divided by divisor. So that's my whole answer when I do the division. Okay, this couple problems are really straightforward. X minus 2 squared we know is a quadratic. We know it's got a 0 at positive 2. And we know it opens up. So it looks like this. Now you have the same thing here, but that's, you can tell if that's a little bit shallower here, or that's going to be a higher degree than 2, so that'd be a 4. So this would be our answer for the first one, C, and then this would be our answer for 47, B. The next one then, the cubic, we have two choices for cubic, or I'm sorry, we have two odd functions here. And then one of them you'll see is like a little flatter right here, so that'd be the 5th degree one. So this would be A, and this would be B. Okay, the next problem wants us to find all the zeros and write the linear factorization again. I would graph this in the calculator to find the rational zero if there is one. It looks like there's a real zero. I'm not sure if it's rational, so what I'm going to do is do second calculate 0, which is 2. Scroll to the left of that 0, and you're going to have to keep scrolling until you see your cursor. There it is, hit enter. Now scroll to the right of the 0, hit enter for the third time, and it gives us negative 1.5. That's good. That's negative 3/2, and that's our 0. We could then take that negative 3/2 and we can divide it in synthetically into this, 2, negative 9 to 30, and we can then get what's left over. Drop down the 2, when you multiply, you get negative 3. When you add, you get negative 12. When you multiply, you get positive 18. When you add, you get 20. And when you multiply, you get negative 30, which is good, no remainder. So what that means is this factors into x plus 3/2 as one of the factors, and then the quadratic is 2x squared minus 12x plus 20. So now we just need to figure out how to do the linear factorization of this. Now this thing's been shifted up 20 units, so we're going to have to use the quadratic formula because these other two zeros, and we can tell that from the graph as well, must be complex numbers, not real numbers. So let's use the quadratic formula on this. Opposite of b plus or minus the square root of b minus 4ac all over 2a. And I can't read my own handwriting, that's a 12 right there. So this would be 144. So this whole thing would simplify to negative 16 all over 2a. And I can rewrite this as 17 plus or minus 4i all over 4. And this is 12, not 17. And then, so I can simplify this. 4 goes into 12 3 times and goes into 4 once, so it'd be 3 plus or minus I. So if I wanted to write the whole linear factorization of this, I could do that by writing x minus this, and then also x minus the other one, 3 minus I. That would be the complete linear factorization. Next problem wants to write a polynomial function with real coefficients, so let's do x minus square root of 5, and then x plus square root of 5, and then x minus 3. Now I have to FOIL this out to get real coefficients, so I'll start with the first two. That gives me, we know it's a difference of 2 squares, so the middle terms are going to cancel, and you're just going to get x squared minus 5. And then I can multiply that by x minus 3. It gives us x cubed minus 3x squared minus 5x plus 15 as my cubic function. Okay, more rational functions. I know we've hit this pretty hard, but I guess here's some more. Vertical asymptotes occur at 0 to the bottom, so we have x equals 1. We also have x equals negative 1. This doesn't factor at all, so none of the factors are going to cancel. Horizontal asymptotes then, ratio of the leading coefficient, y equals 1. Next problem, vertical asymptotes. They occur at 0 to the bottom, so we have x equals negative 3. We also have horizontal asymptote. In this case, actually, there is no horizontal asymptote, but there is an end behavior asymptote if I do the division and throw away the remainder. That's on the formula sheet. So what you'll find is if I do this division, what do I multiply by x to get x squared? That'd be x, follow through, subtract, gives you negative 7x plus 5. What do I multiply by x to get negative 7x? That'd be negative 7. Follow through. And then subtract. And I'm going to get a remainder here of 26. But I can just throw away the remainder. because basically when x gets big, this goes to 0. So there's my slant asymptote. Y equals x minus 7 is my slant asymptote. I know it didn't ask for that. I can call it an end behavior asymptote as well. But it said find the asymptotes, so I guess we should include that. And then it also wants the intercepts, which I forgot to do for this first one. But the intercepts, if we plug in 0 for x, what we get is the y-intercept. And that comes right from the graph, right? And then if we plug in 0 for y, we get the x-intercept. So keep that in mind. So let's plug in 0 for y first into this one. If you plug in 0 for y, you can multiply both sides by x plus 3. We're looking at where the top is, so we're solving this equation right here. We can try to see if this factors, and it does, into x minus 5x plus 1. So our answers for our y-intercepts are 0, 5, and also 0, negative 1. And then our x-intercepts occur where y is 0. I'm sorry, I have to switch these. I plugged in 0 for y, so I found these. So that'd be 5, 0, and negative 1, 0. Here's my two x-intercepts. I'm sorry. Y-intercepts are where x is 0 now. So plug in 0 for x, and you get 5/3. So there's my asymptotes over here, and then also my x and y-intercepts. Okay, we can use our log properties to rewrite these. This would be natural log of x squared minus natural log of y squared. The log of a quotient is equal to the difference of two logs, and I can even bring these exponents down, so I have 2 natural log of x minus 3 natural log of y. And that way it's written as a sum or difference of logarithms. Same thing with this one here. I would make this the log of x to the 1/4 over y to the 1/4, and then change it into log of the top minus log of the bottom, and then just bring down these exponents out front, and you're done. Okay, we can go the other way around, write it as a single logarithm with these two. You can bring the exponents up, so that's 4 and that's 3. And then we can do the difference, so we can have the log of xy to the 4th, don't lose those parentheses, those are important, divided by yz to the 3rd. And you can bring this 4 to both of these and this 3 to both of these, but we've got it as one log now. We can do the same thing here by bringing the 3 up and the 2 up, and then using your log properties to rewrite this as a quotient. This would be to the 3rd over yz squared squared. And I could rewrite this then by making this x to the 9th y cubed over y squared z to the 4th. And 2 of these y's cancel with 2 of these, so my final answer is natural log x to the 9th times y over z to the 4th. And I should have done the same thing here because these y's simplify. So when you rewrite this, log x to the 4th, y to the 4th over y to the 3rd, z to the 3rd. 3 of these cancel, leaving just 1 left, so it ends up simplifying to this. Okay, the next problem wants us to analyze it. We want to do domain, range, continuity, increasing, decreasing behavior, asymptotes, and end behavior. So we talked about all these things individually, but let's put them all together real quick. The domain's the trickiest part. I know you can see from the calculator it looks like it goes from all numbers bigger than 0, and that's true. And if you write it in exponential form as 2, I'll use y, 2 to the y equals 8x. What you can see is that this 8x right here has to be greater than or equal to 0. Actually, it has to be greater than 0 because there's no number that I can put 2 to in order to get a negative number here. I couldn't get 0 either. So that's why you end up getting x has to be bigger than 0 for the domain. So I'll say from 0 to positive infinity, not including 0. That's the tricky part. You can do it algebraically, and you can see it from the graph as well. The range then is negative infinity to infinity. As you can see, this thing does keep going down forever. And you know that too because these are inverses with exponentials, so you switch the domain to range. Okay, and I'm out of time, so here's the rest of the answers to that. It is continuous, it's always increasing, never decreasing. Vertical asymptote x equals 0, and there's the end behavior.